Okay, so I'll bring that information then next week, first class session, and we'll discuss it. Okay, what I'd like to do first of all today is to go back to a problem where we were early on in work and energy, and there was a question that was posed in class, and it relates to this problem back on page 169 that was in your homework. And we had this P force acting against this mass as this mass was slid under the action of that loading, as that mass was slid up the incline here and to where it makes contact with the spring. The question that was posed by Ian was, is the component of that P force that's along the shaft here, is that component, does it behave linearly? And so what I gave you just a moment ago was a handout. So what I'm going to do is pull the book away and place that handout up here. And I'm going to back out a little on the image so we can see this. Okay, so the question posed was, does the component of P that does work behave linearly? So the P force then, the amount of it along this edge here that is moving up through this reversed opposite to this travel distance x is P cosine theta. P cosine theta. So the component of P that's directed along x is P cosine theta, but the cosine of that theta angle is x divided by that hypotenuse geometric length, which is the radical of x squared plus d squared. So there's the cosine times P. Now that clearly is not linear. So that answers the question. The graph of that is right here. If we would plot that component of force, here's what the graph would look like. Now, the work done by that is F dot dr, which is then the component of force times dx. But notice the direction of defined x is down from a fixed reference position here, downward. So I had to assign a negative because the dx is contrary to the direction of the P force. So we set that up as the integral, and then the cosine was that ratio of x over the radical. So the work done by that force P then is written this way. And then we do a u substitution where x squared plus d squared is u. We form the differential of that, which is 2x dx. So what you see in the integrand is x dx, which then has to be replaced by du over 2. When you do that, you get an integral factoring out the constant P force and the negative. We have the integral of this u factor to the negative 1/2 power divided by 2 times du, and we integrate that and we get minus p u to the 1/2. Back substituting the x squared plus d squared for u, we get this expression for the work done between the limits of the initial x distance, x naught, which is where it started, and this final distance where this mass ends up here underneath this d, little d distance. So that it goes to 0 right there. So lower bound is x naught, upper bound is 0. By reversing those limits of integration and reversing the negative here, we end up with this result. And you clearly can look at this and see that this is the force acting times the distance. This was the original geometric length of that diagonal length of cable, and then we subtract off that distance. So it's the change in the length of the cable, which was this minus this. And it was much easier to tackle the problem the way we had originally described it, is just talk about the P force and the fact that it has simply traveled the displacement, which is the difference between this and that. So this is the proof of it, and you can avoid having to do all this calculus by simply treating it the way that we suggested. That seem reasonable to people? Okay, so that clarifies that point. There's another item from earlier in the course that I'll come back at next week with you on kinematics. Okay? So, let's go ahead and move on now. You might use this technique occasionally if you wish to investigate things in work and energy where you have variable component of force like that. You can use this sort of calculus. Okay, so let's come back up to the board. What I'd like to do today is to do the following. Wrap up the angular impulse momentum concept. And remember what this is. This is the change in R cross MV that's occurred. And so we'll do a little wrap up of that and work a couple problems out. And then we'll go on and start looking at direct central impact. And so we'll start to discuss and maybe work a couple problems dealing with impact conditions. So that sort of keeps us on schedule for the rest of the term. And just a couple more weeks left, and we have to get onto some rigid body material real soon. So we're just about done. We're just about done wrapping up the particle kinetics work. Okay? So I think we'll go back to the book and actually work a problem out for the impulse momentum. And I thought we could do something rather basic here. Here's the one we left off with, and I'm going to rotate this. And what I'd like to do is to write down what we ended up with on this problem from the last class session. So does anybody have good notes on the tail end of class last session? Was this the problem? I think it was. Yeah. Somebody have nice notes that I could borrow for a second? I'm just checking on you. Let's see what you got. That's pretty basic. Let's see.
Just the bottom of this.
Okay. Might need my glasses. Okay, so for that particular problem, we had initially, we're looking down again, we're looking as our plan view, looking down from above, and we had this object in motion carrying some momentum, mv on a radius of 0.15 square root of 3. Check your notes. You guys double check that and have notes handy. And then it had some momentum, and this was the initial. This was our initial, carrying this much momentum. So it was carrying angular momentum initially, which we got, and I'd like somebody to punch this up, because I don't think we got to this point because we were running out of time. We have, this is the mass of 0.2 kilograms. This is, I think I cleaned up some stuff here. Oh, actually, I'll tell you what I'm going to do. I'm going to, just to make this work stand alone a little better, let's write down what the momentum was. It was 0.2 kilograms times R omega. And keep in mind that this is the R omega reading combination, and that was 0.15 square root of 3 times the omega initial that this thing was rotating at, which was 4 radians per second. We then pulled the cord that was coming up off the top of that cone and down through the center. We pulled that cord a little bit to cause the object to rise up and move on a smaller radius on the cone surface. And so it's then rotating on a smaller radius now, r sub final, which was 0.1 square root of 3. Is that checked with people's notes? Okay. And then the mass was carrying some new momentum, again, made up of now an R final times an omega final. And that momentum was then equal to the mass, still 0.2 kilograms, times the R, 0.1 square root of 3, times the omega, which we didn't know. Okay, so that was the momentum being carried. Okay, so that's enough to work with now. So these were yours. Thank you. So remember what angular momentum is then. This is the linear momentum term right here, the linear momentum. The angular momentum around an axis that is coming towards us or through out of the board or into the board is a vector. And with our right-hand rule, then, you can see that if you take r vector, which coming from the axis of rotation, outward, our fingers are in that direction, we rotate our fingers in the direction of the momentum, and we get, with our thumb, the direction of that. And so it's coming out of the board at us. So if we call that, well, I'm just going to go ahead and do it. It's coming out of the board at us. So the h about that axis, let me say here's the head of the arrow coming towards us. Let's call that a k axis direction. Then that initial angular momentum is defined as being that r initial vector crossed with that momentum that it initially is carrying. That cross product turns out, since they're orthogonal to each other, and as I mentioned very quickly at the end of the last class session, they're orthogonal to one another, so the magnitude of this angular momentum term is going to be the magnitude of each, the magnitude of the momentum times the radial length times the sine of 90 degrees, since they're at 90 degrees to one another. And that 90-degree sine is 1. So the momentum value is just the scalar product of the terms. So it's going to be the terms you see here times the radial length. So we're going to see 0.15 radical 3 being squared, because we have the radius here as well as part of the momentum, as part of the angular momentum term. And then we have the mass term, and we have the angular velocity. This is very common for circular type of motion. This is m/r squared omega. That's something you'll want to remember. m/r squared omega. Very common for circular motion. Angular momentum term. And it happens to be a vector term that happens to be in the k direction. So we'll assign k hat to that. Is that all right with people? I wanted to make sure we got to that term right there. So that's very common. You can find details about it, more details about it in the book. Then once we're on a smaller radius, it's a very similar structure to that, and we will write that term down. So the angular momentum final is going to be the m again, 0.2, the lever arm or radius of 0.1 square root of 3 squared, and the omega final. Again, it's an it's an m times r final squared omega, mr squared omega, and it happens to be in the k hat direction as well by your right-hand rule. Occasionally you might see a problem where the object might be going this way, and then there's enough force, there's enough impulse acting on it that it actually, like, did you ever play that game where you got the pole as a kid? Tetherball. Yes. Yeah, everybody played that. Some people are better at it than others. I used to get hit in the head with a ball most of the time, but anyway.
You're not the only one.
Oh, okay, I'm glad to hear that. Okay. So anyway, you might have something going around like this, and then what might happen is you might apply an impulse to it, or an impact condition, which we'll study here in a few minutes, and you might cause that thing to turn and go the other direction. So you just got to keep track of the direction. In this case, the angular momentum in both cases is still coming out at us. Okay. Now, the concept that we wrote up on the board originally is that the applied torque in the system, over time is the impulse. Is there any applied torque? There's no friction on this conical surface. There's no friction on the conical surface. Is there any torque applied?
Plenty of force. It's all rate.
Yeah, but the force, if I'm looking down on the cone, the force is in that cable. There's no friction on the surface of the cone, so the force is in that cable, which is this way, and that line of action of that force passes right through this axis of the cone, doesn't it? So there's no applied torque. The axis of the cone is here. The cable tension, the force acting against the mass is right up through that axis of rotation. So there's no applied impulse. That's equal to 0, which means that the change in the angular momentum must equal 0. That is the principle that I mentioned real briefly the other day. This is conservation of what? Angular momentum. Conservation of angular momentum if there's no applied torque to the system. So that means then that we have the change in angular momentum is equal to 0. And if we write the scalar equation just in the direction of k hat, then the angular momentum final must equal the angular momentum initial. So our m, r final squared omega final, must equal m r initial squared omega initial. And the masses divide out since there's no change in the mass in the system. And so the final omega is going to be equal to, is directly proportional to the square of the initial radius times the initial angular velocity divided by, or inversely proportional then to the square of the final radius. So here's a generalized situation if you have conservation of momentum and you're dealing with a circular type of motion. All we have to do then is drop in the numbers, and we should end up with the answer that was expressed in the book. So we had, what was it, 0.3 square root of 3 being squared? Or I'm sorry, 0.15. Square root of 3 squared times the initial omega was 4 radians per second, and our final radius was 0.1 square root of 3 squared. So we lose the square roots of 3, and we end up with 0.0,
2.25.
well, that's 225 with 225, I think it's like that, isn't it? Times 4 over 100th, which is 2.25 times 4, which should be 9. 9 radians per second. Notice that it went from 4 radians per second in its angular rotation, 4 radians per second in its angular rotation to angular speed to 9. This is exactly what you see when the ice skaters do spins, right? Arms out, spinning around at a certain speed, and then they bring their arms in and they spin right on up like a top. Okay? Conservation of angular momentum with no...
4 hours?